A function, for example f of x, is essentially a mapping from one set of numbers, the argument x of the function, to another, the result or value f of x of the function. The fundamentals of this concept are not changed for functions of multiple variables or for functions with complex number or vector results. We can imagine that this set of possible values of the argument is a list of numbers, and the corresponding set of values of the function is another list.
One kind of list of arguments would simply be the list of all real numbers. We could list these in order as the first real number x1 and the second x2 and the third x3 and so on. Of course, for real numbers this is an infinitely long list, and the adjacent values in the list are infinitesimally close together. But we're going to regard these infinities as details, and in the mathematics we're going to set up, we're basically going to presume that we can choose a sufficiently close set of arguments for our function to get a sufficiently good answer. So we will end up working with some large but finite number of very closely spaced elements as the arguments. At least that's the way we will think about it. If we presume that we know this list of possible arguments for our function, we can write out the function as the corresponding list of values that we get. And we could choose to write this list as a column vector. So here would be the value of the function at the first of our real numbers. Here would be the value at the second one, some small distance away from that one. Here would be the value at the third one, some similar small distance away from the previous one, and so on. So we're writing our function here really as a column vector. And for example, we could explicitly specify our function at points spaced by some small amount, delta x. And so x2 would be x1 plus this small amount, delta x. And similarly, x3 would be x2 plus this small amount, delta x, and so on. We would do this for sufficiently many values of x and over a sufficient range of x to get a sufficiently useful representation for some calculation we would do. This is typically what we actually do anyway when we do some calculation on the computer of some function or integrated or something like that. And we could use this approach to calculate something like an integral. For example, the integral of the modulus squared of our function f of x, which is a kind of integral we will often want to perform in quantum mechanics, could simply be written then. Obviously, we could write it out as an integral, but we could write it as the vector product of this column vector and another version of the same vector turned into a row vector in which we put the complex conjugate of all these elements. So if you remember what happens here with multiplying two vectors, this element multiplies this one multiplies this one multiplies this one, and so on, and we add up the answers. And to get this integral right here, we would have to multiply by delta x. So this is an approximation to this integral here, presuming that we've chosen these x1s and x2s and x3s sufficiently close with a small enough delta x. And therefore, provided we choose delta x sufficiently small, and the corresponding vector is therefore sufficiently long, we can get an arbitrarily good approximation to this integral, at least for the kinds of well-behaved functions that we'll be working with. Now, we can visualize a function as a vector. We've drawn a mathematical vector as just a column of numbers here, but we also think of a vector as a geometrical vector. So imagine that we have a function, f of x, and I'm just drawing the function out first of all as this black line, and then I'm marking 3 points on the function. So f of x1, so this is x1 here, f of x2, the green one, and f of x3, the blue one. And we could draw a vector whose components along the 3 geometrical axes are just the values of this function at these 3 points here. So therefore, we could draw this vector here. This is ordinary Cartesian space. We've got our x1 axis, our x2 axis, and our x3 axis, as we're calling them now. And you see that this vector f here has got a little green line as its projection in this x2 direction, so that corresponds to that short line there. It's got quite a nice long blue line here in the x3 direction, so it corresponds to this blue line here, and it's got this quite long red line here on the x1 axis that corresponds to this red line here. So we've basically taken these three heights here and used them as the projection to make up this vector. These different projections here, f of x1, f of x2, f of x3, to make up this geometrical vector. When we've done this, we realize that if we want, we can think of this function as a vector in some space. As long as we only were using three numbers, of course, we can visualize this as a three-dimensional space. Now, of course, in quantum mechanics, one sophistication we have to deal with is that our functions are complex. They tend to have complex values, not merely real ones. And there may be many elements in our vector, or our function, so we have to think about more dimensions here. We may end up having an infinite number of dimensions, not just three, but we'll still try to visualize, at least in our minds, that maybe we can think of a function as a vector. It's a little difficult to visualize this projection here being a complex number, but we'll still imagine that we might be able to think of a function as a vector in some space that is in some way a generalization of ordinary geometrical space. So we still visualize our function, and more generally the quantum mechanical state that it might represent, as a vector in a space. And at least to help us in our own minds, we might keep the idea of an ordinary geometrical space in our heads as we think about functions. We are going to be thinking about functions as vectors in a space. The space is going to be more complicated than this simple geometrical Cartesian space here, but the basic idea we may be able to use to help us as we think about functions as vectors.